Hi, my name is Mike Hawes and I'm an application engineer with Agilent Technologies. And today we're going to demonstrate the seamless ranging capability of the N6785B DC power analyzer on a medical device. We're going to be using a Pulse Oximeter and stepping through a simple 5-step procedure to show you how to do this. If you have our evaluation kit, you already have this device with you. After we go through showing you how to do this device, we're going to give you some suggestions on how you might start with your own device. So let's get started. So step one is configuring the hardware and connecting our medical device. The hardware for our demo today is an N6705B DC power analyzer, and it has 4 separate modules. We're going to only use module number 1, and that is an N6781A Source Measurement Unit, or SMU. So we need to verify that we have the right SMU in our DC power analyzer. I'm going to go to the menu button and use the arrow keys to toggle down to the About selection and hit Enter. Here it describes the different modules that are in our DC power analyzer. And again, I'm really only focused on slot 1. We do have an N6781A there, and that's what's necessary for the demonstration. So the hardware is set correctly. We'll go hit back and go to this main menu. Secondly, we want to connect our pulse oximeter. And you can see that we have 2 twisted pairs here. One is for the output, and we want to make sure that the red wire is on top. And the other one is for the sense, because we do want to use remote sensing and sense down where we're connected to our pulse oximeter. We're basically replacing the batteries in this device. Now moving on to step 2, we need to configure the SMU. So we already have number 1 highlighted. We're going to hit the settings key and look at some of the basic configuration. This is a 2-quadrant power supply, which allows you to sync or source current with a positive voltage. We're not worried about that or most of the settings, but what we do want to do is simulate the 3-volt battery in our pulse oximeter. So I'm going to use again this arrow keys to toggle down to the voltage section, select 3 volts and enter that. If you wanted to, you could change the current limit, but I'm going to leave that as is. There is one other place that I would like to make a selection, and that is in the advanced menu. So I toggle over there, and I go in and look at the advanced menu. I want to verify that we are using the 4-wire remote sense because we have it wired that way. And I also want to check and make sure that we have this output voltage bandwidth set to low. This basically will assume a larger capacitive load on your pulse oximeter and give you a slower response time for the output, which will minimize the opportunity for oscillations. So those look like they're set correctly. We'll go down to close this, close that, and now we've got our SMU configured correctly. Moving on to step 3, we need to set the data logger and configure it. So push the data logger button, and then I come over to our properties button and push that. By default, the data logger sets voltages to be displayed, but I want to look at current of the device. So I'm going to toggle remove voltage and go down and set current. I have 2 other SMUs in there that are also set for voltage, and I want to make sure that those are turned off. So I'll turn those off, and we'll go back to our data logger properties. The other key thing that we need to set is the current log range. As I push this, you can see we have 4 current ranges: 10 microamp, 1 milliamp, 10 milliamps, and 3 amps. If you can see on the slide, seamless auto ranging allows you to range between the 1 milliamp, 100 milliamp, and 3 amp ranges seamlessly, and that means there's no internal relay switching, there'll be no glitches. And so this allows you to dynamically look at sleep currents, which are typically in the microamp level, and up to in the amp level or hundreds of milliamps when you may have some kind of an excitation current needed. This is a patented technique by Agilent and enables you to look at these dynamic currents in your medical devices. So we'll select auto, and then we need to go down and further decide how long do we want to log data. I'm just going to choose 1 minute. And then come down to our sample period, and instead of doing it every 100 milliseconds, I'd like a faster sampling, so I'm going to put in 0.2 milliseconds. Okay, so it looks like our resulting file size that will be stored inside our DC power analyzer will be about 1 megabyte. So we save that, and now we move on to step 4. Step 4 is where we run our data logger. So I've got the data logger set here. I'm going to make a few adjustments. You can see that on the screen we're at 50 milliamps per division. That is appropriate, but I do want to change the horizontal to 10 seconds per division. So I'm going ahead and change that. And I also want the ground level down a bit so that we can see most of the waveform as we're going through the data log. So there we go. We're set appropriate now to run. So what I'm going to do is start the data logger with the run stop key. And that is starting. I'm going to let it go a second or two. And then I'm going to turn on the 3 volts for the SMU. And finally, I'm going to go ahead and put on the pulse oximeter and turn it on. This is going to take about a minute to complete, but you're going to see the current demand from this pulse oximeter as we go through our data log. I'm going to take the pulse oximeter off at about 45 seconds, and you'll see that the current waveform is going to become inconsistent as it's lost the detection, and eventually it will turn off. So we're done with our data log, and we have a display here showing that we've saved the file. So we'll close that. And now let's move on to step 5, where we analyze our data log record. All I need to do is hit the data logger button again, and you can see 2 markers appear. These markers are used to help you analyze the waveform that you're looking at. If you look at the text at the bottom of the display, you can see M1 for marker 1 and M2 for marker 2 tell you what is the current at that place in the time scale. The delta tells you the difference between marker 1 and marker 2. And finally, the min, the average, and the max tells you in between those 2 markers what are the minimum, average, and maximum values. So we're going to use these to analyze the data. What I've set up here first is to look at that spike. That spike is when I turned on the pulse oximeter. And so it was the inrush current that was needed to get it charged up. And if we look at the maximum, or that peak of that spike in between the markers, we can see that it's 275 milliamps. So fairly high level. This would require us to be in the 3 amp range. Again, this is the value of this SMU is these 3 dynamic ranges and being able to change. So now let's move these markers and see what was happening down at the sleep current. So we had 3 volts power applied to the pulse oximeter, but it wasn't turned on. So they're trying to minimize the amount of current here. If we look at the average of this current, it's just 1.4 microamps, so very low drain on the battery. What I want to show is how well and how accurately we can measure that level. So I'm going to change our vertical resolution by 4 orders of magnitude, and we'll take a look at what kind of noise we have down at that 1 microamp measurement that I just mentioned. So I'm going to go back to the previous display and make a few adjustments. I'm going to go up here and put our ground in the middle of the display, and then we'll start cranking down. Okay, so it looks like we're down to about 500 microamps. Let me readjust this to the middle. We'll go down to 5 microamps. So now we've just moved 4 orders of magnitude, and you can see there is some noise here. But if I turn the markers back on, you can see that the noise level is probably about not quite 10 microamps, so maybe 8 microamps of peak-to-peak noise. So we're able to resolve down to maybe tens of microamps at this low level, as well as capture the peak. And I've moved these markers over again. You can see we're still measuring this peak at 275 milliamps. So this is really the value of this SMU with its seamless ranging, and allows medical device designers to look at the dynamic characteristics of their medical device and understand how this will deplete the battery. So now that we've done that, what I want to do is go back through these 5 steps and give you some suggestions of things that you might want to do as you look at your own medical device. So first of all, you want to make sure that you've got the right hardware. We talked about that. You need an N6781 SMU. And then as you're connecting your device, I suggest you use both source and sense. Do the remote sensing out to the device so you get the most accurate measurement. Second, step 2 is configuring the SMU. The main thing to remember when you're configuring that is outputting the voltage that you expect and making sure that you have the output voltage bandwidth set to low. Step 3, configuring the data logger. So when you're configuring the data logger, you're going to need to set that auto range for your current. You remember, this is what sets the seamless ranging. So setting that auto ranging is key to getting the measurement to work correctly. And then of course you want to set the appropriate time frame and sample rate that you're looking for. Step 4, you want to go ahead and run the data logger. Again, you're going to need to look to see what is the appropriate vertical and horizontal ranging so that you get a nice display of what you're expecting to see. And then finally, you turn on the markers, and step 5 is you analyze your waveform. And you can move those markers around to look at the peaks, the valleys, and get a good idea of what's going on as you're using your medical device. So I hope you found this demonstration valuable, and thanks for watching.